So in physics, when describing a motion and how far something went, what its change in position is, there are two quantities that are commonly defined, and it's important for us to understand the difference between those two quantities and what their definitions are, because we're going to be using them. So one of those quantities is distance, which is a fairly ordinary concept. I don't think most of us have heard of distance before. It has a definition in physics that pretty well matches that. It says there's just the overall path length. In other words, it's how far you went. But it says in the slide there, initial position to final position. So in physics, it's often very important when describing a motion to establish what is initial position, what is final position. One way maybe of doing this, if I say, here's an initial position, maybe I call that point A. Maybe over here is a final position. Maybe I call that point B. But if I wanted to say what's the distance between those two, I need to distinguish perhaps like the as the crow flies straight line distance versus maybe what I actually had to do. Like if this was me walking along some curvy path in a park or something like that, maybe I've got my dog and we're just following this path as it curves through, like, I don't know, whatever, grass or something. Or maybe there's a playground somewhere, right? The actual distance I traveled would correspond to how far I went along this path. And in that sense, if I'd laid down maybe some string or something like that along that path, and then I went afterwards and reeled all that string in, and I measured what its distance was by laying out along a straight line, along a ruler or something like that, that would actually correspond to the distance. Or maybe it'd be easier if I just brought an odometer, I guess, to do that for me, right? Contrast that to displacement. Now, in physics, displacement is considered a vector, and the importance of that is that it includes direction. We're going to study vectors in some more detail in a future chapter, but for right now, the main thing to understand is direction is going to be part of it. Displacement, though, is the straight line distance. So if I were to draw a straight line segment going from A to B, as straight as I can get it at least, that straight line distance represents the magnitude of displacement. But given that it is a vector quantity and has direction, I'm also going to represent it with an arrow that points from A to B. Now, the third thing I have here on the key concepts page is a formula, and that really corresponds to a displacement formula. So let me write that over here slightly differently, because that formula I have in the key concepts slide, I think, is maybe the most formal version of a formula for displacement, and it has these little arrow symbols that indicate that those are vectors, and we haven't quite done all the mathematics of that. In one dimensions, it's going to be sufficient to like just remove those and just say, okay, a displacement represented by delta x, which you can think of as like delta x representing change, x representing position. So this is really change of position, maybe on a number line or something like that, but is represented by taking the numerical value of the final position and subtract from that the initial position. In other words, final minus initial is the way that we're going to think about that. The one thing I want to add to this, though, is signs may come up with this. You may have negative positions in that sense. Maybe your initial position is negative. Maybe your final position is negative. Maybe your final position is a smaller numerical value than your initial position, making your displacement negative in whatever coordinate system you're using. So that's going to wind up mattering for displacement, whereas distance is pretty much always going to have a positive value. There's no real way of defining it to have a negative value, in other words.